Hello students, today we are going to derive the expression for resolving power of prism. Last time you have seen here, the resolving power is the ability of optical instrument to produce two images of nearby objects. If the nearby objects are not seen by our eye, their two objects can be appeared as a single object for our eye, and that nearby objects or the nearby spectral lines can be seen separately by means of optical instruments or the optical devices like prism, grating, etc. Now today we will derive the resolving power of the prism. Resolving power is the ability of optical instrument to produce separate images of nearby spectral lines. And for that here, consider this figure. In this figure, this is the prism. The A is nothing but the angle of prism. Here the T is nothing but the base of the prism, and L is nothing but what here? The length of the side of the prism. Now here the S is nothing but the source of light, which contains the two nearby wavelengths or the two closed wavelengths, lambda and lambda plus d lambda. This is nothing but the slit, and this slit is illuminated by the source of light which contains the two wavelengths. L1 is nothing but here the collimating lens. Exactly slit is placed at the focus point of this lens, so the outcoming or here going rays are parallel. So parallel beam of light is incident on this prism. The A is nothing but here the width of parallel beam of light here. The alpha is nothing but the angle made by this incident beam of light with the prism. Now here, when this light is incident here, the rays are dispersed here. The two rays are dispersed because here we are getting the two images of slits, that is I1 and I2. Due to the I1 and I2 in this figure are the two images of slit due to the wavelength lambda and the lambda plus d lambda. Here is also written, this is I2 corresponding to lambda plus d lambda, I1 corresponding to what here? The lambda. So these are the images of the slit or the two nearby spectral lines. If the source contains two wavelengths, we are getting two spectral lines, and these are closed spectral lines. We are getting two closed images, I1 and I2 are getting, and corresponding diffraction pattern of the I1 and I2 are also shown here. Now if the source of light contains the white light, if suppose white light consists of the 7 colors, that is ranging from violet to red, that is ranging from 4000 to nearly about 7000 angstrom unit, and that wavelength can be visible to our eye here. And here we can use the two. If the white light is used, we are getting here the 7 images, I1, I2, I3, I4, etc. up to 7 up to red here. So if the source of light contains the two closed wavelengths, we are getting here the I1 and I2 are the images of the wavelengths corresponding to wavelength lambda and lambda plus d lambda here. Now this is L2 is nothing but the focusing lens. So these rays, refracted rays or the dispersive rays, are here collected at this point I1 and I2. This is L2 is nothing but focusing lens, L1 is nothing but what here? The collimating lens. And here I1 and I2 are the images or the spectral diffraction pattern of the two spectral lines is shown here. Now the RP of prism is defined as the ability of prism to produce separate images of two nearby wavelengths or the two closed wavelengths lambda and lambda plus d lambda, and mathematically it is defined as RP is equal to defined as it is RP, this resolving power RP means this can be defined as the average wavelength, that is lambda, divided by difference in wavelength, that is nothing but what here? The d lambda. And if suppose this is the equation number 1, so mathematically RP of prism or the RP of grating can be defined as lambda divided by lambda plus d lambda. Lambda is nothing but the average wavelength of these two wavelengths, lambda and lambda plus d lambda. We will take the average wavelength, that is lambda, and d lambda is nothing but what here? Difference between the two wavelengths here. Now according to Rayleigh, two nearby spectral lines are here are said to be just resolved or the just separate if the principal maximum of one diffraction pattern, this is the diffraction pattern of I1 and I2 is shown here, corresponding here, and when the principal maximum of one diffraction pattern falls over the first secondary minimum of the other diffraction pattern and the vice versa, then the two spectral lines are said to be just resolved, and this just resolved condition is shown, and also prism is set at minimum position. Minimum deviation position is set here, and this is the Rayleigh's condition. Or the principal maximum of other diffraction pattern falls over the first secondary minimum here, then these two spectral lines are said to be just resolved. So this is the principal maximum of I1 here, at same position this is the first secondary minimum of other diffraction pattern. When it happens, then the two spectral lines are said to be just resolved here, and this will here occur only when path difference, the path difference between the two rays, path difference, or we will say PD, path difference, this should be equal to integral multiple of the wavelength n lambda, where the n is equal to 0, 1, 2, 3, etc. here, and which gives the order of diffraction, that will give rise to the order of diffraction here. Now in this case, so before going to that, if suppose this is the spectral line and the diffraction pattern, if we will say here, this is the principal maximum, we are getting principal maximum followed by secondary maxima and minima, and intensity goes on decreasing like this. So in the single slit experiment, it is clear that the diffraction pattern of a single slit, that is I1 or the I2, these are the images of this slit. So consist of I1 and I2 also consist of the principal maximum here, and it is followed by the secondary maxima and the minima like this. So in this case here, it is equal to 0, and this is the first secondary minimum, this is the first secondary minimum, this is the second secondary minimum here, and so on. In this also, this is the first secondary minimum, this is second secondary minimum, and so on. So from this to this here, and it is here the n lambda, n is equal to 0 here, and corresponding values of the lambda here is nothing but the lambda, here is nothing but what here, the 2 lambda. So we have to put here the n is equal to, in this equation we have to put n is equal to 0, we are getting principal maxima. When n is equal to 1, we will put, we are getting the first secondary minima. If n is equal to 2, we will put here, we are getting secondary minima particularly, and so on here. So this is the principal maximum, and this is the first secondary minimum. We will concentrate on this, and this is nothing but here the path difference. This is equal to what here, the path difference, and value of the path difference in this case, because according to Rayleigh's criterion, the principal maximum of one falls over if suppose this is the other diffraction pattern, if this is the other diffraction pattern suppose, and the principal maximum of the other diffraction pattern must be here, maximum coincide with the first secondary minimum of the other, and here the first secondary minimum of this should fall on what here, the principal maximum of the first. So this much is nothing but what here, when this will happen, or this Rayleigh's criterion is satisfied, the path difference between these two, this is suppose the I1, this is I1, and this is the I2, then path difference between these two must be equal to lambda. So because we will put here n is equal to 1, or in this case, this is above is general equation. So for here n is equal to 1 for first secondary minimum, and here the path difference should be equal to what here, the lambda. And in order to determine now the path difference here, in order to determine the path difference, consider this figure, and here draw the normals. These are the two rays, dispersive rays or the refracted rays. One is indicated by the dashed lines, other is indicated by the solid lines here, and we are getting image. Draw the normal from this point to on this solid ray as well as dashed ray here. So we can draw the normal. You have to remember that this is the angle, d delta is nothing but angle of difference between the angle of deviation between these two rays. Delta is nothing but angle of deviation corresponding to wavelength lambda here. The alpha E is nothing but angle of prism here, and so on. here. Now draw the normal to determine the path difference here, like this, normal to this ray as well as normal to this ray. So what we are getting is, here we are getting the angle. So this angle d delta obviously and this d delta is the same. Now, and the path difference here we are getting I1 to I2 distance here is equivalent to this, because this upper ray travels distance this much, this below ray travels the distance up to this. So there is path difference here from this to this. Here this is the path difference that we have to calculate, and from this figure we are getting here. So we can apply here the path difference. For that we will sin d delta, this will be equal to sin d delta. We will consider this is the right angle triangle, and you have to remember that here these two sides are taken to be the same. This is the A, this can be taken as A, this is the right angle, this is the hypotenuse, this is side angle, and as here this is d theta, which this is, we will consider this is the arc like this here. So A and E, this side also the A, so this side divided by hypotenuse can be regarded as A. So path difference sin d delta will be equal to here, here the path difference, whatever the value of the path difference divided by the hypotenuse, that is equal to A. These sides are equal, this can be considered as arc, and we are getting here DE. Now we will take this, rearrange this, as this d delta is very small, the sin theta becomes theta, and therefore it can be regarded as d delta. This d delta is equal to path difference divided by the A, as delta is very small. So we can write like this, sin theta becomes theta, and from this equation we can write AD delta, this will be equal to the path difference. So we can put this value AD delta here. So AD delta, this will be equal to lambda, and d delta, which implies that here d delta. So this d delta will be equal to lambda divided by what here, the A. This is equal to lambda divided by A. So we will also require that equation. We will write here the d delta, this will be equal to lambda divided by A, and this is suppose the equation number 2c. Now from figure we can write here. So what we can write is, from figure here, this angle is nothing but pi angle. This is the total angle here. This is nothing but here the pi 180 degree, and this is distributed as alpha here plus A plus alpha plus delta. So this alpha, so consider from this figure, this alpha plus A angle of prism plus again alpha plus delta, and this is equal to what here, the pi, that is 180, that is equal to what here, the 180 degree. Now which can be written as, from this, 2 alpha is equal to here A plus D, we will take to that side, so pi minus A plus delta, here the A plus delta. Now which implies here the alpha is equal to, this alpha is equal to pi by 2. We will take this 2 to this side, minus A plus delta divided by 2. Now we will take the sign of both sides. So sin alpha is equal to sin alpha, this will be equal to sin of pi by 2, this is pi by 2 minus A plus delta divided by 2. We are getting like this. But sin of pi by 2 minus theta, sin of pi by 2 minus theta is cos theta. So this will be equal to cos of, we can write cos of A plus delta divided by 2. This is because sin pi by 2 minus theta, this is because sin pi by 2 minus theta this theta will be equal to cos theta, is equal to what here? Cos theta, and therefore we can write like this equation. Now again from figure, this sin alpha we are getting. So consider this right angle triangle. So consider which right angle triangle? So consider this right angle triangle here. So from this right angle triangle, this is hypotenuse. Here the A sin alpha is equal to front side divided by hypotenuse, that is A divided by L. L is nothing but length of side of the prism. So here the sin of alpha is nothing but here we are getting A divided by L. So we are getting this equation also is full. So I will write here. So A divided by L, A divided by L, this will be equal to cos of A plus delta, A plus delta divided by the 2. So suppose this is the equation number 3. This is the equation number 3. Now we will recall, also we can write here the one more term is required, and that is sin A by 2 is equal to, sin A by 2 is equal to, again from this figure, sin A by 2, sin A by 2 is equal to, from this equation here, this is consider the right angle triangle, this sin A by 2 is equal to front side t divided by 2, here the t divided by 2 whole divided by, this is hypotenuse, and this is nothing but what here? The hypotenuse. This is the right angle triangle. So this is the right angle triangle, and from this right angle triangle we can write here the sin A by 2. Sin A by 2 is equal to front side value t by 2. This is the t is base of the prism. Here is nothing but normal is drawn. It will be divided into 2. So t by 2 divided by the L. So this is divided by the L. So from this equation we are getting here, this we will take 2 to denominator. So t divided by 2L. So we are getting 2L, and this is the equation number 4. So we are getting these equations 1, 2, 3, 4. Now recall the well-known prism formula, and that formula we are knowing mu is equal to refractive index of the prism formula, mu is equal to sin. This is sin A plus delta divided by 2. This is the well-known prism formula, whole divided by sin A by 2. It is sin A divided by 2. Here means nothing but refractive index of the prism, and which implies we will take sin A by 2 to this side. So we are getting sin A by 2, sin A by 2 into mu. Here is equal to sin in bracket A plus delta divided by 2. We are getting this. In this equation, this mu and delta depends on the PVlll. And so what we have to do is that here we will differentiate this equation with respect to lambda. So for that, this is the constant term, as it is we are getting differentiating. So differentiating we are getting differentiating above equation with respect to lambda. So in this equation mu and delta depends on lambda. So sin A by 2 a constant as it is remains. So we are getting sin A divided by 2 into differentiation of this, we are getting d mu divided by d lambda. With respect to lambda we will take. So this is d mu divided by d lambda, and this will be equal to, now differentiation of this sin of some angle, that will give rise to cos. So cos of A plus delta divided by 2, this is the differentiation of sine. Similarly, we will take the differentiation of angle A plus delta by 2. Here A by 2 plus delta by 2. A by 2 constant, differentiation 0. So we will take the differentiation of dw 1 upon 2 as it is. So here we are getting 1 upon 2 as it is, and differentiation of angle, that is d delta divided by d lambda. So what we are getting here is, this is the differentiation. Now we will put the values, all these values. We are knowing sin A by 2 is equal to t divided by 2l. So from these equations, all these equations, from equations 2, 3 and 4, this equation become sin A by 2 t by 2l. Here the t divided by 2l we are getting into this term as it is d mu divided by d lambda here. So this will be equal to value of cos a plus delta by 2 is equal to a by l. It is equal to a by l. So this will be equal to a divided by l here into half as it is. Here the value of d delta is equal to lambda by a here. So we will put here the value of d lambda, that is lambda divided by the a, and d lambda kept as it is. So we will take as it is. So this will be implies that here. So this will be equal to these two get cancels. These two get cancels. L also get cancels. Here a get cancels, and what remains is here the t into d mu divided by the d lambda. This will be equal to lambda divided by d lambda. Again from equation 1, it is seen that here from equation 1 lambda by d lambda is nothing but RP of prism, and therefore we can write here the t as it is into d mu divided by d lambda. This will be equal to, this is nothing but RP of prism. So this is the RP of prism. This is the expression for RP of what here the prism. So this is the required expression for the RP of prism. So RP of prism, it is seen that here the RP of prism depends on here the base of the prism, length of the base of the prism, that is t, and the another term, that is d mu by d lambda, and the term d mu by d lambda is called as dispersion produced by the prism. So it is seen that if this t increases, the length of the base of the prism increases, resolving power increases. And so it is seen that d mu by d lambda means here the d mu by d lambda is equal to dispersion produced by the prism. The ability of prism to disperse the rays, the RP of prism also depends on that factor. This is because when you are getting the narrow spectrum, this resolving power is less. If you are getting broad spectrum, angular separation is large, then also the resolving power is increases. So this is regarding what here the resolving power of the prism. Resolving power of the prism depends on the length of the base of the prism and the dispersion produced by, that is the material used by the, we can use d mu by d lambda means here the prism is made up of the material. If the material is very nice, so that we are getting the angular separation between the different colors is large, then also RP of prism increases. So this is regarding the RP of prism. In the next lecture we will see the RP of grating. Okay, thank you.